This is 971's 2014 robot. So what do people notice about this robot?
Is it spring? Wait, that's spring loaded? Just shoot? But okay.
Yeah, so 2014 had the big
Okay.
ball. Yeah, so big extension springs back here. Lots of extension springs.
Are the rollers on the bottom keeping the ball in place? Or am I just... Yeah. Well, if you like do angle adjustment.
I believe, yeah, those spin.
Okay.
Which I believe this is, the name of this robot was Mammoth, and these were the Tusks.
Oh.
Big brain.
What other features on this robot like stick out? Starting, I guess, like down at drivetrain, probably.
It's weird shape. Like
Yeah.
it's fatter.
So I think this photo has it better. So it is a, it sometimes misrepresented as a hexagon, but really it's an octagon.
Yeah.
There's a short, flat-ish section on each side here, right? So what would be a potential reason for having weird shape? Any ideas?
More stability with when handling like the big wall.
Oh wait, what was on? Wait, hold on. Continue what you were saying. Or
No, just that it would be like more stable. Or maybe more stable like on the side, so it doesn't tip over sideways.
So yeah, so you do get a wider. Yeah, your center is wider, so it would be harder to tip over sideways. That is true. So also not necessarily why, but also just how are they able to do that? So it wouldn't make much sense to do that in a game where your sizing box is confined to a certain box, right? So like for many years, we were defined to a 30 by 28 by 38 rectangle was as big as your robot could be. And then we've gotten recently, many of the years have had a frame perimeter, right? So 2014 was one of the years where you had a frame perimeter, so you have some total number you have to hit, right? You take a tape measure, wrap it around the entire exterior robot, and you can't be more than, I think this year was 120, but it could have been it was 120 because 2013, I believe, was 112. But that may be off a little bit. I haven't looked at that robot in a long time. So what is making this not a rectangle do? You do get a little bit of stability that way, right? But you could, in theory, have side-to-side stability there, but you could still have the same width, but then you would just have to make it not as long, right? If you want to keep the perimeter at whatever the number is. What am I trying to say? So if you have, what is the difference of the different shape get you in terms of like your robot area, or I guess your overall total robot volume? If you have a shape that is a 100-inch perimeter circle versus a 100-inch perimeter square or rectangle, which one has the most area?
Wait, a circle or a square?
Yeah.
Circle?
Circle?
Yeah. So a circle with the same perimeter as a square will have a bigger area. So in theory, you have more room inside your robot if you make a non-rectangular robot. But that's not the only reason. So how would these like angled sides interact with other robots on the field?
You'd like slide off them easier.
Harder to defend against that robot.
Right, because if we were trying to like push them sideways, when we try to drive in, if we don't catch them right on this little like small sideways bit, if we catch them on one of these angled sides, now we're not really pushing them sideways. We're pushing them at some different angle to their wheels, right? So they always, if you catch them on this angle, they almost always have some way that they can drive away from you that's not perpendicular to where you're pushing them. And so, because that's one of the best or hardest defensive maneuvers to get out of is the T-bone pin, right center. If you just push somebody on their side, it's very hard for either robot to leave if they're Omni, or if they have like 2+2 sometimes allows you to kind of pivot out. You have Omni wheels on one side because you don't have that the scrub from those wheels. But this way, they're never really pushing perpendicular to tires, so you can always kind of drive away. So there are a couple different teams who are running some version of this for a little while. It's kind of somewhat gotten out of fashion. It hasn't been, not too many teams have been running hexagon and octagon bumpers, frame perimeters for a little bit. I'm sure it would come back at some point. What else? So yeah, so we mentioned that the Tusk, these like tubes spin, so you can kind of see the gears up here that's showing them spinning. So these are able to spin in and kind of that, like we said, they're center of the ball. What else? If you were just describing how this robot worked to someone who had not seen it, what would you tell them it does?
So the claw, yeah. So then the claw helps pick it up with these wheels. Does the whole spring thing, is that what like pushes it out?
Yeah, so that like so this like disc here, they pull this back and then this is they release it to punch the ball out of the claw and into the goal. So that's how they launch it.
I saw in one of the other photos, I think, was the thing chain driven for tension? The spring?
Yeah, so like, yeah, so there's the chain run here. So as they pull this back, they're pulling, like these are the springs when they're in there, like,
gotcha, yeah.
right? So when they pull this chain back and those springs extend, and then you have like the little pneumatic thing up here that you can imagine is some sort of a latch, right? It's going to hold it, and they release it to fire it. So what's this main, like how do they actually aim the ball, right? So like it wouldn't make any sense if they just intake it here and then fire it into the ground. That doesn't make any sense, right? So what are they doing? So they have these two claws and they have this big sprocket here. So what is that doing?
Angle adjustment for the shooter.
Yeah, so this whole assembly, right, these two claws and this whole catapult spring assembly, puncher, whatever you want to call it, is able to rotate. And we'll see in the video in a second when I pull up the reveal, it actually flips all the way around so they can shoot out the front of the robot, out the back of the robot. And they can intake from both sides. I think that they intake better from this side when the wheels are up, but they can grab on that side. Let's see. Everything else relatively standard. It's kind of the older control system. That big gray thing right there is the old kit of parts compressor. It's a lot heavier than the one we run now. Okay, so what was the other thing I was going to say? Okay, so one of the things that's hard to see from the picture, and it makes way more sense when you see in the video, but like you see this tube here running to where the tusks are, right?
Mm-hmm.
Then it has this angled one coming up to where this bar is. In this photo, it comes up, and then it looks like it's straight here, right?
Mm-hmm.
So that means at some point they're different. So what we'll eventually see in the video is these two claws are actually independently powered. So this sprocket over here is driving this top one, I believe. I think that's right. And this sprocket over here is driving the bottom one. And then one of them is mounted to the shooter. I don't remember which one. I think the bottom. Yeah, it's the bottom because you have this rail in here. So these bottom tusks are mounted to the shooter. So the top one is independent. and can kind of clamp the ball separately. I think the reveal should be there is interesting. All right, I guess we'll watch their season highlight video.
I found 3 more books here.
Lots of little rivets. Birthday. I didn't see it. There was a picture I wanted to get to. Okay, so it was harder to see from those photos, but here's where for like this front side of the drivetrain, you have your front and back wheel in this plane, and then they use that space they had for their kind of the bumper push out and everything to have they have a bigger wheel as their center wheel, and it's further out, like it's wider out than their front and back wheels. So they can kind of use that space, and they get the gearbox kind of packaged in here a little bit more. So they can use the space a little bit efficiently, and they still have all of these like folded over sheet metal parts. It's all really thin sheet metal, but they can get a lot of strength from having all those flanges built into there. Okay. Yeah, so that's basically what the robot did a lot of. They were one of the better finishers, whatever you want to call it. So they would be the last robot, and they would shoot into the high goal. They were very good. They were on our division in 14 at Champs. And then Citrus took, in my mind, the decision for Citrus was either them or 11-14, and Citrus took 11-14. Which worked out. They got to be world finalists. But 971 was very good as well. So yeah, so looking at 971's CAD, where are some of the more unique things that you couldn't see before? So we can hide some of the shielding. Yeah, they have all the CADed springs. That's cool. It's a lot of detail. So I believe, so yeah, so they have some some of these holes are slotted so they can belt tension by like unscrewing or unriveting these somehow. I'm not exactly sure what they did there. Maybe there's bolts and then this block helps do the tensioning too. Something like that. I'd have to dig in a little further to see exactly how that works, but I'm pretty sure that this bolt right here is some part of the tensioning mechanism. I'm not entirely sure exactly how. It may not be fully in CAD either. Okay. What else? So there's some form. This whole launching mechanism is super complicated. I've never quite done the whole deep dive on how this one works. But you can see the biggest thing is there's a lot of reduction, right? They have these two motors into a pulley, into a gear reduction, into another gear reduction, into another one. So you're 1, 2, 3, 4 stages. So a lot of gear reduction, and you have this big, rather large plate back here. That is, so this is their brake caliper. So that's a brake caliper off of like a bike, or sorry, this is the brake disc. And this model here is the brake caliper. Getting good brake caliper CAD is hard, so it's roughly the right geometry, but this would be like what's on the, mounted on like a mountain bike or something. Then they have a bolt and a pneumatic cylinder, so when this gets pushed up, it clamps the disc and holds it. When they release, it lets this spin. And there's some other latch up here. Oh, so this little board is a sensor. So this is how they know it's pulled all the way back, I believe. So that's, it like detects a magnet. Let's see. Yeah, so in here, there's another cylinder, and this latches to something, but it looks like it's being weird in CAD because this, I don't know if that block is real. Is the block real? I feel like that block's not real. Okay. Maybe it's real because I don't know what mounts to this now. Yeah, I am unsure. Does that move? No. Yeah, somehow something along here releases and this whole thing's able to slide. I'm not sure what releases. I probably have to look at that a lot more. One of the things,
it kind of looks like a clamp, and I don't know, that little, wait, hold up. Like, can you go to the side view?
the back view or the other side view?
Maybe something with this one, because that kind of looks like.
Oh, so I think that just holds the spring.
Okay.
So those get bolted in. Yeah, so those get bolted over the springs. You see the spacer? So that's where the spring is held in place. So there's like a full going through that, and it's clamped. So that's not going to release anywhere. That's a nice method for how to do that. Where's my maybe clear? No. How do I get rid of all of the annotations? Do I not have that power? Oh, clear all drawings. Okay, there's another button on the clear. Now I'm just confused. Okay. Yeah, somewhere in there there's a clamp. I'm not sure exactly where or where that slides on. That may just be some somewhat oddity of the CAD. And they have them up here too. They have clamps for where the springs mount up there. Let's see, another more gear reduction here. So it goes belt into a gear into a final stage chain. So they use, you know, most of the motion transfer methods all really close together. You get belt pulley, gear, and sprocket. So they do partly, so why would they want to do this, right? So what's the benefit of having this long belt run to your motor down here?
Instead of like having your motor just up there.
Yeah, like, right, because they could have done it like instead of doing this belt run, they could have done a gear, right? They already have gears here. They could have done another gear reduction right here. Why would you not want that?
Is that too much weight up high?
Yeah, so that's one reason, right? So you don't want this, back then we're using sims, so these are pretty heavy. You don't want that up here. But another reason, if this sim was mounted up here, when this arm tries to flip over,
Oh yeah, I'm just hitting
yeah,
it.
that doesn't work at all, right?
Yeah.
So bringing it down both brings your center of gravity down to get your weight lower, but it also clears out all this space because they couldn't, in their design, like in like the space restrictions for this robot, basically nothing that didn't move, anything that didn't move couldn't pass this sprocket, right? So that's why all of this is clear. Same with figuring out how, like, exactly how high this cross member is, right? If they weren't going to swing all the way under, they would almost certainly want to bring this higher, as you're going to make this a lot stiffer across. But they couldn't do that otherwise, because this whole assembly would have hit these things, right? So these are placed very specifically so that this back assembly, when it swings under, doesn't get hit. Let's see. So the other useful thing, I believe, there's the way they do chain tension up here is based on this block. I'm still not entirely sure. Oh, there you go. Yeah. So they can move this whole like printed block inside this cap. If that makes sense. So I don't think they catted it. They did not. But basically, where this is like, it looks round right now, this would have been an oval. And these 4 bolts, I should not have hit something. Okay. So this block, when you tighten these 4 bolts, you can bring this up, which makes this sprocket go further away from the smaller one that it's attached to. So you can tension the chain by bolting in these 4 bolts. I believe that's how it works. I think they go over this, I believe, in their designing robots for control presentation that Travis does for one of their Spartan series. And so everything is spinning on this shaft, but this shaft is not spinning, right? So this shaft is just a long dead axle with everything and bushing on it, and only the sprocket mounted to each arm is the thing actually spinning. Sorry, on shape is always tricky. Yeah, so that's how you get this kind of pattern where you get the U here, and you get this other U over here. So this side is mounted to this sprocket, and this side's mounted to that sprocket, with these kind of middle beams just rotating along nicely. Let's see. Each of their tusks, does each have their own motor? I don't actually know. Yeah, it looks like it. So each of the tusks have their own motor. So they would be able to, in theory, set each of these to different speeds if they wanted to. If I'm not mistaken, I believe these are just painted PVC pipes. I don't think there's anything special. I do not know how they mounted these. Oh, there we go. I had never actually, this is diving into this robot. I've never seen this part before. So they made kind of like a special hub that went into this gear, I'm guessing. Yeah, so they drilled into the gear and made a special hub, and they brought out this kind of tube on it to support it so that it wasn't flexing too much, is my guess. And they just bolted into the hub from the side here through the piece of PVC to be able to turn it. Yeah, and the screws into the hub are coming in from the back here, because you have these countersunk screw places. So then these holes would have been tapped. Cool. Okay. I don't think there's anything too crazy in the drivetrain. It's like, I mean, it's a complicated sheet metal drivetrain, but it's nothing all that different. Oh, there's a good example. We haven't looked at too much of how the dog shifters work. So this is, actually, it's both dogs in there to show the different states. If I hide one, the pneumatic cylinder grabs this and either engages this gear or engages this gear, by actually like slotting them in. So it's a different way to get a high and low gear. Okay. Anything else that we didn't go through on this robot people want to dive into? Yeah, so their intake, a couple different motors on a belt. Oh, so this is kind of cool. So they do a, it's a single belt for both motors. And then to be able to tension it, they have this pulley here with a bolt and nut on this side and a slot. So then they can just kind of drag this forward to bring this closer in and then lock this tight. And you get a single belt on both those. And each of the pulleys has over 180 degrees of wrap, which works nicely. So this is something we haven't done very often. We haven't made a lot of complex pulley paths. Most of ours are just center distance pulleys. But this works well. It can save you some room, right? Because the other option would be to like have to do the same thing. You would need like offset motor mounts or something to get the belts side by side, to go to like a double pulley over here or something. Where this lets you do it a lot cleaner, fewer parts. You have to deal with the tensioner, but that may be good, right? Because if you do end up, if it changes tension for some reason, you can set the tension however you need it for your intake. And then from there, it's just gear to the 2 sets of wheels, or to the wheel set, and then another belt going forward. Okay. Any last questions? All right. That wraps up.